Welcome. Today we'll be taking a look at the notes worksheet entitled Rational Expressions Day 1. We've been focusing our attention on the polynomial family of expressions, so it's time to just switch gears and deal with the rational family of expressions. When you think of a rational number is a number that can be written as a fraction. And so that's what we'll primarily be looking at here, algebraic expressions written as fractions. So let's go ahead and get a couple things on your paper here, just a little definition, I suppose, just a description of what we're going to be looking for, and then we're going to do a little simplifying and a couple of the operations today. So let's start it out there. A rational expression, I guess the best way for me to describe it is just, it is a quotient, so division essentially, a quotient of two polynomials. And I guess there's one little catch to this, so I'm going to go ahead and put it in place here. So quotient of two polynomials, in terms of the denominator, we want that to at least be a degree 1 polynomial. So denominator must be at least degree 1, and I'll show you why in just a sec there, but that's how I would describe that piece. I think I'll give you just a little example, kind of put in just so you can see it, although obviously there are examples all throughout this particular notes worksheet. So an example might be something like this. I'll just go ahead and create a fraction essentially, so division. And I don't know, numerator something like x squared plus 5. So polynomial in the numerator, and then polynomial in the denominator. Again, I would characterize that the denominator must be at least a degree 1 there. What we don't want, if you remember from polynomials, we don't want a constant down there, which would be degree 0. So this, and don't write this on your paper, that as having a degree 0 polynomial on the bottom wouldn't be characterized as a rational expression. So that's just why I put that one piece in here. And hopefully that makes sense. Again, shouldn't be a big issue. We'll see these throughout the notes worksheet. Okay, so again, there are a variety of things we're going to do with these rational expressions. Really, I can envision 6 good things. So the first is going to be simplifying. The second will be multiplying. The third will be dividing. And then you'll see the other 3 components to this on the Day 2 notes worksheet. All right, so let's get into the first order of business, simplifying a rational expression. And by simplifying a rational expression, it's essentially reducing a fraction. And so I'm going to just write it like this. So our expression will be simplified or reduced if the numerator and the denominator have no common factors, and that's going to be the key. Everything is about factoring with these in order to simplify them. So underline that piece if you would. No common factors. And so I think it would benefit us a little bit at least to investigate the nature of factors and when we can reduce and when we can't. There's so many different little red flags that go into dealing with these expressions, and just wanted to caution you on them as best as I can. So there is a little investigation to get us thinking, as concrete as possible, as straightforward as possible. But what you need to do is transition this idea into the more abstract. So the investigation. When can you cancel terms in the numerator and denominator? Well, guys, very simply. If I asked you to reduce 6 over 9, in your mind, obviously, you'd immediately just say 2/3. But the reason for that, of course, is this piece right in the middle. So 6 is a product of 2 factors, 2 and 3. 9 is a product of factors 3 and 3. And because you have a common factor in the numerator and denominator, they can essentially cancel out. And when they cancel out, you're left with the 2/3, and hence your answer. So notice in this case, common factor of 3 can cancel. Absolutely. So just throw a little yes right in there without question. Now what if I sort of took this piece? Instead of 2 times 3 and 3 times 3, I had a plus in between. And the question, of course, I would have for you is, can you cancel out the 3's and have this just be equivalent to 2/3? Well, if you look at this numerically, 2 plus 3 is 5, 3 plus 3 is 6, so this is 5/6. And is 5/6 equivalent to 2/3? No, of course not. So a big fat no right in here would do. But you would be shocked and appalled how many times, just as we're dealing with abstract expressions, students will do exactly this piece. They will try to cancel out something along these lines right here, but as you can see mathematically, it's not viable. Okay, so just please be very cautious about when you can and when you cannot cancel out terms in the numerator and denominator. Okay, let's draw a little conclusion from this, and let's get into just some problems dealing with it so you can really see it. Again, I know you see this piece right here. That's not the issue. The question is, can you then expand that knowledge when you see it into more abstract expressions? Okay, let's get it in. So you can only cancel a term out if it is separated by multiplication. That's what it means to write things as factors, and that's the premise behind really this entire notes worksheet. So you can only cancel a term out if it is separated by multiplication. And I'm just going to highlight the idea. That's what we mean by factors. So factors are a product of terms. Okay, so let's give it a try here. I'm going to try to have you take the bait on a couple things you can't do, but let's see if we can maintain and make sure whatever we do is mathematically legitimate. All right, so simplifying to start. A couple strategies just that I wrote on your notes worksheet. Take them for what they're worth here. So number one, write the numerator and denominator as a product of factors. Absolutely. So before you decide to cancel anything out, ask yourself, have I factored it completely? And then, of course, cancel out any common factors in the numerator and denominator. Perfect. All right, example one. Let's just simplify each rational expression. And so I've got this piece right here. And I would ask you right off the bat here, because it does look pretty tempting, can I cancel out the x squareds, one on top, one on bottom? And the answer is absolutely not. Don't cancel those out. And the reason I can't is because of that plus right in here. So this is not, well, I should say the x squared is not a factorable term that can cancel out with that x squared down there. All right? So just make sure before you do anything with this expression, factor it. Well, let's factor it. It looks like in this case we're probably talking about a GCF here. Greatest common factor, it looks, according to my eye, looks to be 3x. And then as a result, take out the 3x, and I'm hoping you see that you get a 5x plus 8. So what I did is I took this sum of two terms right here, and I wrote it as a product of three factors. The 3 times the x times this linear factor right here, 5x plus 8. Okay, perfect. Now the bottom just happens to be a monomial, 3x squared. It's up to you. You don't have to do this. I think of it as a product of 3 times x times x. That's what x squared is. So again, sometimes I do this just to be dramatic, but notice separated by multiplication. And now as it is factored, things are ready to slash and burn here. So the 3's, they can go. The factors of x, notice on both sides separated by multiplication. So they are truly factors common to the numerator and denominator, they can go. At this stage, I'm left with 5x plus 8 over x. And of course, I would ask you this one, can I cancel out the x's right here? There is one on the numerator and denominator. Can they cancel out? And no way. No, please do not cancel those out. Again, this x is part of a larger factor. That x is part of the 5x plus 8. So you cannot just cancel it out. It is not an independent factor. There you go. That's how it will play. Let's move over to letter B. So a little harder in terms of our rational expression here, but let's see if we can make it work. So first order of business, because it does look nice, can I take the 4x to the fourths on top and bottom and slash them away? Nope, because they're separated by the plus. I haven't factored anything yet. Nothing is written in factored form, so don't even think about canceling anything just yet. Be great for you to kind of pause and see if you can factor this one by yourself, or you can play it out with me if you'd like. But I notice the numerator looks like it has a greatest common factor to it, and that looks to be 2x squared. Take a look at that if you get a chance. Make sure you see. So a 2 from those and an x squared from those. That's looking good. And then looks like I'll have a 2x squared plus the x. And how does minus 3 sound? So good start. Pulled out the greatest common factor. I might have to play around with this one a little more, but oh well. And then denominator, actually, as a matter of fact, numerically looks like I can pull out a 2. In terms of the variables, looks like I can pull out x squared from everything. So 2x squared is looking great. And I get a 2x squared. How about a plus a 13x? And then a 15 on the back end there. That looks great. Now, I do see a couple things that I can start to cancel out. And if you want to cancel it out at this stage, you are more than welcome to. I'm going to go with the frame of mind that I don't cancel anything until everything is completely factored. So I'm going to keep a few things and then just work from there. But I hope you did notice that we do have a quadratic trinomial in the numerator, a quadratic trinomial in the denominator. We should be able to factor them. So great practice for you as well, especially with these quadratics with an a value other than 1. I would love to see you pause the video and see if you can factor them fairly fast, but I see this kind of going like that right there. And denominators, same thing, 2x squared. A couple binomials side by side would do it. All right, well, I'm going to go ahead and just factor it the way I see it. And obviously we're talking about a 2x and an x. And we need factors of 3, so 1 and 3 or 3 and 1. And it looks like I'm going to have the 3 here, just from what I see. And plus 3, and then the minus the 2 would give us that. I'm seeing that as our 2 factors. Hopefully you did that already, and that looks good. And in the denominator, same thing. Looks like I have a 2x and an x right here. Factors of 15 we're going to need. And so same order of business. I'm hoping a 3 and 5 split will do. And that'll give me a 10x and a 3x, and that should do it. Nice. Now notice what I have. I have factors on top, factors on bottom, and I think we're ready to roll. So 2's, yes. Both factors of x, yes, absolutely. 2x plus 3's, yes. Notice again, everything that I cancel is separated on both sides with multiplication, so it's truly, everything is in factored form. Now I'm ready to go with the x minus 1 and x plus 5. Do the x's cancel here and make it negative 1/5? No, 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 of course not. Absolutely not. Notice those x's are separated with plus and minus, so you can't do it. Awesome. All right, so just working with those, simplifying it out, not too bad. Factor, factor, factor. All right, so next order of business is to take a look at the 2 operations here, multiplying and dividing. And in order to do this, really it's just a natural extension of what we just did in the previous example. So it really shouldn't be too bad at all. So strategies, of course. And number 1, factor each numerator and denominator. Notice, cancel out common factors. And then if you remember kind of working with fractions in middle school, we're multiplying just straight across there once that's done. 2 and 3 theoretically can be switched, but you go with what works for you. This shouldn't be old news. Okay, here we go. So I've got this rational expression times this one. I'm not just going to multiply it straight across and develop this big quartic on the numerator and a quadratic in the denominator. Remember, you see this a lot in mathematics as you go through the levels. You do want to break things down rather than build them up. We want to simplify if possible. And so that's what we're going to do right here. Those are the strategies that we're going to utilize. And so very much like example 1, I'm going to factor. I'm just going to go ahead and do it 4 different times. Left numerator, left denominator, right numerator, right denominator. That's all. So let's start with that left numerator. Okay, and again, feel free to pause and do this on your own if you'd like, or just follow suit. But I see a difference of 2 squares right here. So I'm thinking of 3x and 3x, 5 and 5, plus and minus, and just check that, but that looks pretty good. And then I just keep moving. Bottom left, what do you see in terms of factors? It looks like we can pull out the 2, and x minus 1 should do. Very nice. Working right across, there's my times. And x plus 1, x minus 1 on this difference of 2 squares right here. And looks like I have another greatest common factor situation. Pull out the 2, and how does 3x minus 5 sound? Now notice, everything here is separated by multiplication. Even this, even across the fractions, it's all multiplication. So the beautiful thing about this, everybody, is anything on the numerator that is also on the denominator can cancel. It just so happens this one cross cancels. 3x minus 5s can go. This one cross cancels, x minus 1s. Again, it's all separated by multiplication, so it can go. Here's a good question, just as I'm looking at this. Can the 2's cancel? No, of course not. Because in order to cancel, 1 has to be in the numerator, 1 has to be in the denominator. They're both in the denominator, so you're just going to multiply them across. So at this stage, what I personally do is just push the things that are left across. So I've got this times this. So 3x plus 5 times x plus 1. And then 2 times 2, I'll at least go ahead and do that and get 4. If you want to multiply this out and get a nice quadratic trinomial out of it, you are more than welcome to. It's not necessary, though. I'll take this as a good answer. All right. So there you have it. Let's go ahead and do letter B. Again, I'd encourage you to just pause and see if you get these right as we go through them. But I'm going to just, it's all multiplication here, 2 fractions. And in order to work with this, I'm going to see if I can break them down and cancel stuff out. So x minus 1 squared on that top one. Done. Pulling out the x right there. And by the way, I would ask you this, of course. Does x squared plus 1 factor further? No, not in the real number system. So leave that. That one's prime. And then times, looks like I'm going to pull out the 4 and get another x squared plus 1. And you start to see, if you break these down appropriately, I'm sure good things will happen. And then how about this last one here, just a quick quadratic trinomial, looking good. All right, let's let it ride. Anything on the numerator and denominator, x minus 1s, slash them. X squared plus 1s, slash them. And that's looking great. Anything else that you see? No, I don't see anything. So numerator now, just push them straight across. At this stage, again, just number 3 here, multiply them across, x minus 1 times 4. And if you decide to distribute the 4 in, more power to you. Not necessary, though. We'll see certain situations where that might be beneficial. For our purposes here, this is perfectly fine. And that's good. All right. So notice the strategies kind of play out nicely with example 2A and B. So just make sure you do see that. Before you cancel anything, just ask yourself, have I factored it? All righty. Let's go get the third component to today's lesson, which is the division. And this is just really a review question from middle school. What must you remember to do when you divide rational expressions? And just hoping that you remember this piece. So essentially, dividing by a fraction is the same as multiplying by its reciprocal. And so that's essentially what we're going to do here. Change the operation to multiplication. And flip the second rational expression. Awesome. So again, it's that component of dividing by a fraction is the same as multiplying by the reciprocal. And the reciprocal occurs when we flip that second rational expression. So I have an example 3 here, just going through the motions with the same ideas, just one little extension, that's all. Now I'm going to go ahead and do this. If you don't feel it's relevant here, that's perfectly fine, but it is the first one with division, so I feel obligated to go ahead and do exactly what I wrote on the board earlier. Change the operation to multiplication. There we go. So it's the first rational expression times the reciprocal of the second rational expression. So I flip it, x cubed minus 8 moves to the top, x squared minus x minus 12 moves to the bottom. That looks awesome. Now is it exactly like example 2? Of course. So let's see how you can do with this. Be great. Before I get to it, see if you can factor that one right there. It does factor. All right, well, I'll start with that. X plus 3 is just a linear factor, prime. Not much we can do there. Difference of 2 squares, so x plus 2x minus 2. Got my multiplication symbol right in between. I'm going to do the bottom first, just give you a little more time if you haven't done that top right already. I'm seeing x minus 4x plus 3. And just like this was a difference of 2 squares, hey everyone, this is a difference of 2 cubes. So hopefully that pattern, is really starting to click. So x minus 2, and then it goes x squared, x times x squared, of course, for that, plus 2x to get some things to cancel, and then negative 2 times 4 would give me the negative 8. There you go. Awesome. Notice it's all factored, so everything is separated by multiplication here, even in between the two fractions, so it's ready. X plus 3's, goodbye. X minus 2's, good riddance. Anything else? Nope. Remember, this quadratic is going to be prime, and that seems to be the only thing that's left. So x squared plus 2x plus 4 in the numerator. And how does x plus 2 and x minus 4 sound in the denominator? As said, if you want to go ahead and multiply that out, you're more than welcome to, of course. No issues. All right, there we have it. Good. All right, so letter B is just some good practice with some of those quadratic trinomials, especially some of the more complicated ones. I'm going to just set it up for you and then ask you to pause the video and try factoring at least a few of them. You don't have to do all 4, I guess, necessarily, because I'll put them up there in just a few minutes, but it would be great to see nonetheless. All right, so let's just see what we've got. It looks like this rational expression divided by this rational expression right here. Looking good. So I'm going to go ahead and get it going in terms of changing it to multiplication. And there are a couple little tricks when it's written like this, but ultimately, dividing by this fraction is the same as multiplying by its reciprocal. So I take that and I just flip it. So the 8x squared plus 10x minus 3 comes on top, and the 9x squared minus 6x plus 1 goes down on the bottom. All right. So at least it's ready to go in a nice visual way here. The only thing to do at this stage is to factor and then cancel anything out. And again, if you factor appropriately here, I do believe good things are going to happen. All right. Well, I'm going to go ahead and get mine set up for you. I seem to remember that this one is just binomials galore. There we go. Here's the time for you to pause a little bit, maybe work off to the side if you use my method from a few lessons ago to work with these quadratics. However you were able to do it, but we do need you to get to be able to factor some of these quadratics pretty well. Well, let's see if you did it and how you did. Top left, I have 3x minus 1 as a factor, 3x plus 2 as a factor. Bottom left, I have 4x minus 1 as a factor, and 3x plus 2 as a factor. Top right, I have 4x minus 1, 2x plus 3. And last but not least, this one looks like a perfect square trinomial. Oops, let me get that sign right for you in there. So I have 3x minus 1, 3x minus 1. All right, looking good. So the question, of course, is what can go? Well, again, everything is separated by multiplication, even in between, so we're good. We can and do want to cancel out 3x minus 1s. 3x plus 2s just happens to be in the same rational expression, just like when we started this lesson, so those would simplify. 4x minus 1s, and it all looks really nice. Looks like our final answer, just a linear factor on top, linear factor on the bottom. Looking great. Okay, nicely done. Okay, everyone, let's go ahead and hit sort of the next piece. So I said there were really 3 components to today's lesson and then 3 components to tomorrow's lesson. 2 of those components will be addition and subtraction of rational expressions. And I have to tell you up front, addition and subtraction represents an entirely different process than the multiplication and division. So we're going to have to totally change our mindset from what we did see today. So we do need to be careful. That's going to be the hardest part of these particular lessons here. Make the distinction between the 2. Multiplication and division one way, addition and subtraction another. Well, of course, in order to work with fractions in addition and subtraction, I hope everybody does remember and realize we are going to start talking about least common denominators. So we do need a common denominator to add or subtract fractions. And in what that represents essentially is an idea for finding least common multiples of those denominators. So when we talk about LCD, you probably have seen that before. Least common denominator, really what that represents is the least common multiple of the denominators. So I have a couple strategies here to get us thinking about it, especially when it becomes more abstract. But let's see what we can do. So I'm going to just quickly read, I guess, and then we'll do a very concrete example just so you can see that process unfold, and then B and C, obviously, a little more of an abstract way to look at it. So number 1, in terms of the strategies, break down each term into a product of prime factors. So prime factorization is a little trick that comes up a lot in number theory, so we're going to do a little prime factorization on these. And then I just kind of work left to right. And what we want is the least common multiple. So that's this piece right here. We don't want repetitions from our different lists. And you'll see this unfold in just a sec. So we want not just a common multiple, but the least common multiple. So we're going to have to avoid any redundancies. All right, perfect. Well, let's go ahead and start the process of prime factorization. That occurs essentially with a couple branches leading down from the number. And what we want to do is break it down into its prime factors. So 6, very simply, can be written as 2 times 3. 2 is a prime number, so circle it. 3 is a prime number, so circle it. All right, very nice. Now everybody, if you would, the 8. 8 can be written as a product of 2 and 4. So let's go ahead and just do a couple branches on that 8, 2 and 4. 2 is prime, everybody, so circle that. 4 is not prime. It can go further. And so 2 factors of 2, and we circle those as well. So it is the circled values that are our prime factors of 6 and 8. And guys, what I'll ask you to do is just throw a little vertical curtain in between our 2 lists there. And here's how it basically plays out. I'll slow it down just a touch so you can kind of see this piece. Now, what I'm going to ask us to do is just work left to right. And if I come across a number that happens to be in the exact same number in the other list, we're going to cancel it out. So for example, does everyone see this 2 right here? I want this 2. It is a prime factor of 6. but I see the exact same 2 in the other list. And so this is a redundancy of that right there. And I don't want it twice. Okay? The 3, obviously, I do want the 3, and there are no redundancies of the 3 in the other list, so I keep them. The 2, obviously, I keep the 2. If there's a 2 in the same list, I want both. I don't cross out stuff in the same list. I only cross out in the opposite list. So one more time on this. When I took this 2, I had to cross off the exact same 2 in the other list. This is a redundancy of that. That's how it's going to work. Now, by the way, I should have asked you up front, if I asked you for the least common multiple of 6 and 8, you're thinking, what number does 6 and 8 divide into? What is the lowest number that happens? And I'm sure you would agree that it's 24. 6 goes into 24, 8 goes into 24. That is the smallest number that occurs. Notice what I get right here when I include all my prime factors. 2 times 3 times 2 times 2. And when I multiply those together, everybody, of course, I get 24. And that's the key. Now here's the idea, just real quick with this piece. Just want to do one more thing here, and then we'll go get letters B and C. If I accidentally forgot to cross out this redundancy right here, and I included that 2, that would be another 2 out here, and 24 times 2 is 48. Hey everybody, is 48 a multiple of 6 and 8? Yeah, of course it is. Is it the least common multiple of 6 and 8? No. And that's the idea. Okay, so cross out the redundancy. All right, let's go try it on more of an abstract level. This just happens to factor beautifully as a difference of 2 squares. X plus 1, x minus 1. If you want to circle, you're more than welcome to. I don't know, sometimes I don't do it when it gets more abstract. This one right here factors nicely, x plus 1 and x plus 1, x plus 1. Nice, and circle both. Looks good. So at this stage, I put my little vertical curtain, 2 different lists, and then I just go ahead and work straight across here, left to right. And if I take one that happens to be in the other list, then I cross out the redundancy. So I'm looking at that x plus 1. Does everyone see that x plus 1 right here? Do you see the exact same x plus 1 is in that other list? I don't need it twice. So this particular factor is identical over here, and I only need it the once. So I take that, x plus 1. I'll take the x minus 1. I look for a redundancy. Nope. And I keep going. There was another x plus 1. This one was identical to this, but this is another x plus 1 that I do need, so I keep it. And just in terms of the way this is written, x plus 1 times x plus 1 is x plus 1 squared. So as a result, again, hoping you kind of see this sort of bear out from this when we do it concrete to abstract, that would be the least common multiple of these 2 expressions. Great. Let's try one more. And if it's not clicking just yet, don't sweat it too much, because we'll go ahead and look at this obviously on the next notes worksheet when we actually get into the addition and subtraction. So this one I see factoring is x plus 2, x plus 3. Go ahead and get those in. And again, you don't have to circle them at this stage, but I do. This one right here, it looks like you pull out the 3, and then you get x squared minus 4. And please feel free to arrange this any way you want. So the 3 is definitely a prime, but the x squared minus 4 actually does go further. X plus 2 and x minus 2. Prime and prime, so that's good. I do this myself. I'll just go ahead and put a little vertical curtain in between. And then, as I said, I just work left to right. I would love for you to pause for a sec and see if you can pull this off. What would be the least common multiple of our terms based on the prime factorization? Well, I take the x plus 2, but notice this x plus 2 is identical to this one right here. I don't need it twice. So I take it, cross that out, and then just keep working. X plus 3, not 1 over here, so that's good. Take the 3 and take the x minus 2. And there you have it. Least common multiple of this and this. Do you want to multiply that out? No, of course not. Leave it as it is. All right, so we'll definitely build on this idea in the next notes worksheet. So if it's clicking, great. You'll be fine heading into it. But I do know on the next notes worksheet we start off with a review example to get you going and thinking in the right direction. Well, thanks for listening to the lesson there. If you have questions, of course, please don't hesitate to ask. And try some of those practice problems.